Hello, my name is Christophe de Bruyne and welcome to the first in a series of lectures on knowledge representation on the web. These lectures are based on the course material I have developed over the years for the course on open information systems at the Vrije Universiteit Brussel. In this first lecture, we will introduce the notions of an information system, an ontology, the role of ontologies in open information systems, and then introduce the role of ontologies on the semantic web, which is a specific application of ontologies. Information systems on the web are, in general, developed and maintained autonomously. In this picture, you see the various actors, entities, and components of a generic information system. The development of an information system is driven by the context of the organization and its requirements. A conceptual schema, which captures the concepts, relationships, constraints, and instances relevant to an organization, needs to be developed. That conceptual schema, depicted on the right, is key as it will be used to create a database schema to store and manage the information and parts of the interfaces. Now, where does the conceptual schema come from? Well, the conceptual schema is a result of various stakeholders reaching agreements on the universe of discourse, which are then put into a design tool by a designer, usually a computer scientist, a software or database developer. Important to note is that those agreements are reached with natural language. The stakeholders communicate with each other. A domain expert will observe the real world to identify abstract concepts and relations key to the enterprise. Notice that the real world is partly inside the context of an enterprise, as some of these concepts and relations only make sense within an organization, but not outside. An example would be an employee identification number. The end users will engage with the system and test effects they encounter in the system with reality. Any input is then used to evaluate the system and, if need be, to refine the information system in a subsequent iteration. Now, how does that conceptual schema relate to the real world? Well, there are two types of interpretations. The first is an intentional interpretation, allowing you to map symbols from the conceptual schema to concepts and relations in the real world. For instance, the concept person, person, corresponds with a natural person in the real world. An information system will also capture and store information about instances in a database. That database can be used for the second type of interpretation, the extensional interpretation. That information can be mapped onto specific things in the real world. For instance, a record about me, Christophe de Bruyne, somewhere in this world. It is important to note that the same schema can be reused, and you can therefore have multiple different extensional interpretations. We all have a calendar, yet our calendar entries are different. Many information systems that have been developed autonomously share concepts and relations, but they may look different or they may be represented in a different way, which is called semantic heterogeneity. Now, what if two or more such information systems need to interoperate meaningfully? Well, in that case, maybe because of a merger, they need something to mediate the information between the two systems. And that something will be called an ontology. But first, what is semantic interoperability? Well, Pieter de Leen here defines semantic interoperability as the ability of two or more information systems or their computerized parts to exchange data, knowledge, and resources, and to be able to interpret the information in those systems. Now, for information systems to interoperate semantically, an ontology is needed. And what is an ontology? Well, an ontology is commonly defined as a formal explicit specification of a shared conceptualization. Conceptualization is the thing that we invoke in our heads when we think about a concept or a thing. Like, I have an image, a mental image of a cat, and I will try to make that explicit in a specification. And I can draw that on a piece of paper, I can write that in prose, but unfortunately, those things cannot be understood by a computer. That's why the definition was extended with the notion of formal. We need to avail of things that are grounded in logics and mathematics so that computers can reason over them. Now, for me to create an ontology on my own, it doesn't make sense. Therefore, the community has also added the notion of a shared conceptualization. We need to come to a mutual understanding and make that understanding explicit in order for interoperability, semantic interoperability, to be successful. Now, this definition implies that an ontology captures the agreements among all the stakeholders. And ontologies will evolve while agreements are being developed. We might agree at one point, but as we further develop the ontology, we might come to the realization that there's a misunderstanding, which we need to clarify and rectify, and that might have an impact on the ontology. And in the end, ontologies will become an externalization of the semantics outside an information system. So what will happen when two such information systems need to interoperate in a meaningful way? Well, they will send delegates, representatives of their information system that will constitute a community. The community will look at the real world they share and interact with each other using their natural language to come to the necessary agreements that will finally result in the ontology. That ontology will be used to replace their shared world, and that ontology will enable semantic interoperability by annotating application symbols in their respective systems so that that information can be shared via that ontology. Now, engineering ontologies is difficult, and we will see that we will need appropriate methods and tools to support this activity. In these lectures, we will avail of Protégé as an ontology engineering environment to create ontologies for the semantic web. Ontology engineering as an activity is defined as being the set of activities that concern the ontology development process. That includes principles, methods, methodologies, tools, languages, and whatnot. I like to pinpoint an important distinction, difference between a method and a methodology. Method is a way of doing something, whereas a methodology is the study of methods. Now, ontology engineering methods may be covered later in this course. If you're lucky, an ontology already exists that you can use. But what if that's not the case? Well, one approach is to look for resources that can be considered near ontologies, such as thesauri, lexicons, glossaries, gazetteers, which contain a bit of structure that you can convert or align into an ontology. Another approach is to engineer them from scratch, top-down, by availing of subject matter experts, starting from the more abstract concepts towards the more specific concepts. Another approach is to mine them from suitable sources. That's a bottom-up approach. You use existing resources such as databases and lift them into ontologies, or consult non-structured resources such as text in order to elicit facts from them. Now, here's a specific example of a near ontology, the SAP glossary. In this screenshot, you can see that we looked up the definition for rack meter, which is considered a specific type of meter that measures the amount of product pumped into a truck. Now, that glossary contains a little bit of structure, and we can elicit information from that. So if we were to conduct the exercise, we could see that in that particular context of SAP, a rack meter is a meter is attached to a rack meter is measuring the amount of product pumped into a truck, and so forth. Now assume we have a conceptual schema or a database schema, and we need to map that onto an ontology, but the ontology doesn't exist yet. Can we create an ontology out of a conceptual or database schema? Yes, we can create parts of an ontology using those artifacts in a process called lifting. We will identify the parts of a conceptual schema that are relevant to a domain, so not enterprise specific, and we will map them onto symbols in the ontology. So it's basically, the process of lifting is basically an identity mapping from symbols in the conceptual schema to the ontology, but we will do that by cleaning the symbols through a vocabulary, for instance to avoid jargon, We will leave behind the constraints and enterprise-specific knowledge, as I said before, and we may be adding extra domain-specific relations or relationships not present in the conceptual schema. An example of that would be the relationship is adult. A person is an adult if that person is at least 18 years of age. That is something that is not necessarily captured in a conceptual schema, yet may be relevant for our ontology. Now, when we don't have a conceptual schema, but only a database schema, we need to consider that the database schema only has a very flat view of our world. So before we lift directly into an ontology, we need to identify the things that have been lost in the translation of a conceptual schema to a database schema. So when we lift a database schema, rather than going directly from the database schema to the ontology, we will think about the concepts and relationships in our database schema and add on to that what has been possibly lost. And that would then constitute the lifting of our database schema. A thing that I forgot to mention on the previous slide is when you lift a database schema into an ontology, you have to take into account any possible encodings that has happened when the database schema was created. What I mean by that is certain database technologies impose certain restrictions that has an influence on how you represent things in an information system and your database. Technologies might impose that column and table names might not be longer than 12 characters, resulting in database developers choosing names that might not seem that intuitive and might not be appropriate for an ontology. So at the bottom we see a very simple database schema with only one relational table representing people. We keep track of their first name, they are identified by an ID, and then there are a bunch of columns representing an address, and it's optional. Now, important to note that in the database schema, we don't really know what the relationship between an address and a person is. It's implied. Are they born there? Do they live there? We do not know that. Now, a database schema is often derived from a conceptual model. And here we have at the top an example of such a conceptual model. We now see that a person is still identified by an ID and we keep track of their first name, but a person lives at most one address, and every address belongs to at most one person. Now, this is an example. This is often not true in real life. Of an address, we keep track of their street, city, and country. We also see that in the conceptual model, address is modeled as a weak entity. It is identified by certain relationships, and in this case, the relationship with a person. So every address is identified by their person. And when we derive a database schema from that conceptual model, we might end up with a database schema that only contains one table instead of two. Why? The existence of an address depends on a person, and we don't keep track of complex relationships other than those with people in the conceptual model. So all the attributes of an address are grouped into the table person. Things are a lot easier when you have a conceptual schema from which you derive the database schema, but quite often you will find that these conceptual schemas do not exist. And yet we have to account for a particular problem. In a relational database schema, we only keep track of the things that we are going to store. And a lot of the semantics are gone. Remember, this particular address has a relationship with a person, but we don't know what it is. Hence, when you lift a database schema into an ontology, there will be this intermediate step where you have to figure out what the relationships between all the things are. So let's go back to our conceptual schema and use that as a basis for an ontology. Now, what could we remove from that schema or change so that it becomes a suitable basis for an ontology? Well, first, it is very unlikely that the artificial ID for a person is meaningful outside our information system, so we can leave that behind. We can then look at the various constraints in our conceptual schema. We have stated that an address is identified by people, which is very likely not true in the real world, so we should remove that constraint. Now, maybe each address does not belong to exactly one person. We can have multiple people living at the same address, so we can get rid of that constraint. The other constraint might also be not true in the real world. Maybe each person can have multiple addresses. They can have second residencies or even third residencies. So depending on the purpose of your ontology, it might be sensible to leave that constraint behind as well. Now, what can we change? Well, it can be that due to legacy, we've called the relationship between people and addresses lives at. But it might be replaced by something more meaningful in the ontology, by, for instance, resides at, because being a resident, that relationship has a legal bearing. So we would change this into resides that. An important distinction to make is the difference between relation and relationship. What is the difference? Well, a relationship is an instance of a relation. Take, as an example, the relation friend of, which is abstract. The fact that Hugh Jackman is friends with Ryan Reynolds, that's an instance of said relation. Let's now talk about term and concept complexity. Some terms and concepts are known and recognized by everybody, while for others, the definition of one term introduces the need to define other terms. A simple example of the former is Tweety. We all know what concept that term invokes. An example of the latter is open market value. Open market value has been given a definition from a particular reference work, this one, and it's quite complex. I will not go over the whole definition, but you can see here that the definition refers to other terms such as amount, property, willing seller, and whatnot, which might need to be defined as well in order to properly comprehend that definition. Now let's talk about relation and relationship complexity. The definition of a term often requires the specification of relations to other terms and rules on these relations to constrain their meaning. Again, these can be simple and complex. Here's an example of a simple one. Tweety is a bird, where Isa is a relationship between Tweety and bird, just to denote that Tweety is an instance of bird. A complex one is Christophe is a resident. In the context of Ireland, you have to meet certain criteria in order to be considered a resident for tax purposes in that country. So what are the differences between an ontology and database and conceptual models? Well, ontologies are supposed to be shared even though they're developed autonomously. Remember, if an ontology isn't shared within a group of stakeholders, it makes no sense. Ontologies are furthermore independent of any specific application purpose, yet they're often obtained from specific context and domain. Ontologies are furthermore supposed to be language independent because they're artifacts to be processed by computers, yet they are the result from engineering processes in which stakeholders use their natural language to reach the necessary agreement. Ontologies furthermore translate into difficult new requirements. To what extent are ontologies supposed to be standardized? How open are ontologies supposed to be? How extensible do they have to be? And then there's the matter of scalability, both in terms of design and implementation. A good example is a trade-off between reusability and usefulness. An ontology with terms and relations that is highly constrained for a specific purpose is highly usable. However, the number of constraints is likely to render it not as reusable. That trade-off and other aspects are elaborated on or described in the following paper that I would encourage you to read. So ontologies are created for the creation of so-called open information systems. Now, what are the difference between open and, let's call them, closed information systems? Well, closed information systems are designed for the purpose of one organization. The requirements and functionality are known beforehand, and the data model are agreed upon locally and refers to organizational concepts, which do not necessarily make sense outside the organization. All facts about the domain are already stored. Facts that are not stored are presumed to be false, which is something we will call later on the closed world assumption. And they're typically stored using proprietary software or in a way that is generally only understood by the designer. Ontologies for open information systems, however, on the other hand, are developed for deployment on the internet or the web. They're domain-specific but not application-specific. That's a slight nuance. The usage contact applications are largely unknown beforehand, but sometimes you cannot determine or control how it would be used outside these. And ontologies refer to language and context-independent concepts. One important application domain of ontologies is the so-called semantic web, or the meaningful web. On the web, we as humans can interpret the relationships denoted by hyperlink, often implied. That task for machines is much more difficult. Now, what is the semantic web? Well, the semantic web is defined as being an extension of the current web in which information is given a well-defined meaning, better enabling computers and people to work in cooperation. That basically boils down to representing content on the web in a way that is more easily machine accessible and to use intelligent techniques to take advantage of these interpretations. Intelligent techniques can include classification, inferring implicit information from explicit information, discovering relationships between concepts, and so forth. The semantic web is realized by using a bunch of standardized technologies that constitute the semantic web stack. There are many variations of the semantic web stack, but the gist of all of them boils down to the same thing. Here's one published by W3 Organization in 2007. Most of these technologies we will cover in the lectures. We will be using URIs and IRIs to identify things. We will be using the RDF data model to capture relationships between things. Now, that data model needs to be serialized in some way. We will be using either XML, N3, or Turtle to serialize those relationships. The RDF data model itself is not really an ontology language. In order to accurately describe our universe of discourse, we will be needing ontology languages. There's a simple one called RDFS, RDF Schema, that allows us to create type and role hierarchies. If we need something more expressive in order to infer contradictions in our knowledge base, we will avail of the web ontology language. We can also describe parts of our domain using rule languages covered here. Now, all of them are stored in RDF as a data model and serialized in whatever serialization format we will be using. To query those relationships, we will be using the standardized query language for RDF called Sparkle. Now, this concludes the first lecture. The goal of the first lecture was to explain to you what ontologies are in general. Towards the end, we've seen a specific application of ontologies, namely the semantic web. I do admit that things are still quite abstract. In the second lecture, we will be covering the RDF data model, where things will become a lot more tangible. Here's a bunch of papers that I've referred to in this lecture. If you're interested, I would highly encourage you to read the first and the last paper in order to learn more about ontologies and the grand vision of the semantic web.